This is Potla Siri from MSc Ed Physics 12th semester RI Mysore. In this video we are going to discuss about cluster beam evaporation, in which it is one of the approaches of preparing a nanoparticle. Now coming to the index of this video, first of all we will be discussing about the introduction about a nanoparticle, what is actually meant by nanoparticle, and the next one is different types of approaches that we have to determine a nanoparticle or to prepare a nanoparticle, and the next one is vapor deposition technique. It is one of the technique which is used to determine or which is used to make a nanomaterial, and in this video we will also see what is its contribution to our cluster beam evaporation. And the next one is our final topic, which is cluster beam evaporation. So in this content we will be studying about how it is constructed, what are the materials used, how it will be working, and its principle also. And the next one is its comparison with all other different approaches. As we have studied the different approaches, what is its comparison with other approaches, and at last we will be studying about its advantages and disadvantages, mainly limitations of this cluster beam deposition. So now coming to the nanomaterials, what is actually meant by a nanomaterial? A nanomaterial is something, a material or any substance in which at least one of its dimensions should be of a nano range, that means of 1 to 100 nanometers. For example, if you consider this as a nanomaterial, at least one of its dimensions, either this or this, should be of a nano range, which is of 1 to 100 nanometers, and 1 nanometer is equals to 10 to the power minus 9 meters, which is also different from the bulk materials. It may be a physical, chemical or optical property. The bulk material will be different from the nanomaterials. You can also see here we have 0-dimensional, 1-dimensional, 2-dimensional and 3-dimensional nanostructures also. And next, coming to its properties, the first property that we are going to study is high surface to volume ratio, which means if the material is decreased to reduced to a nanostructure, its volume will be increased. Like for example, if you have taken some liquid which is of a unique liters or unique volume, if assume that it is a paint, if you are able to paint single wall of a room using that bulk material, if the same bulk material is converted into a nanomaterial using the same volume, you can easily paint the entire walls or all 4 walls of the room. So it means whenever a material is transformed from bulk to a nanostructure, its volume, its surface to volume ratio, that means using the same volume we can able to spread the surface area. And next, other one is quantum effects becomes important. We all know that classical and quantum theories are two different branches, in which classical theory will mainly focuses on the concepts which are related to a bulk material, and a quantum which will be mainly focused on the nanoparticles or very tiny particles. So when we discuss about classical theory, for example, if we take energy band or any other bands in our classical mechanics, it will state that energy band of any element or atom, it will be continuous. But when it is stated in the same way in quantum effects, it will easily determine each and every rotational and vibrational levels of each and every material. So it will become more important to study about anything in nanostructure. So its quantum effects will become more important. And the next one is changes in its properties. As we have already discussed that the properties of the nanomaterial which is already formed using a bulk material will have the different properties than like from the bulk material. For example, if its shape and size will not be exactly same or similar to that of the bulk material from which it is formed. And the next one is enhanced its electrical conductivity. So depending upon this surface to volume ratio, the electron dispersion will be more, like it will be spreaded over a large surface area, in which scattering of electrons will be very less, so that it will enhances the conductivity, electrical conductivity of the material. And the next one is its higher mechanical strength. Higher mechanical strength in the sense, a bulk material, it may have different defects in it, like some holes, some cracks will be present inside it. But if the same material is transformed to a nanomaterials, those kind of cracks or some kind of damage inside the material can be reduced. And the next one is better chemical reactivity. These small nanomaterials will sometimes work as a catalyst also, which will increases the rate of the reaction, in which it will make the reaction to happen very fast or quick. And the next one that we are going to discuss about is the approaches of synthesizing the nanomaterials. And majorly we have two types of approaches. One is top down approach and the other one is bottom up approach. As you can see here in this picture, see, the top down approach is something in which you are starting with the bulk material, then you will reduce it into a powder, then you will prepare a nanoparticle. And bottom approach is something you will be taking the material which is of nano size and you will make it into a cluster of bunches of clusters, and these bunches of clusters are combined together to form atoms or molecules. And the next one we are going to study is about vapor deposition method. This vapor deposition method is of two types. One is physical vapor deposition and the other one is chemical vapor deposition. This deposition is something in which the physical nature of the material will be changed. If it is in solid state, it will convert into liquid or vapor and then it will deposit on the substrate. So if it is physical vapor deposition, this entire process will take place in the physical form by changing its nature from solids to liquids to gaseous. But in chemical vapor deposition, some kind of chemical reactions will be taking place depending upon by controlling the temperature, pressure, all these things. Some chemical reaction will take place so that the material will be deposited on the substrate. So now the next one is about the comparison. We are just comparing our top down, bottom up approaches and its physical chemical approaches by our cluster beam evaporation. So before understanding this, we should understand what is actually meant by a cluster beam evaporation. This cluster beam evaporation is first of all a bottom up approach, in which you will be considering a nanoparticle initially, and that nanoparticle will be combined to form a cluster. So these combined clusters, these bunches of cluster will again combine to form n number of atoms or molecules. In a cluster, we may have easily 2000 to 3000 atoms. As you can see, it is a bottom up and physical deposition approach, in which the material, the material from which we wanted to make a nanomaterial, that will be of a physical form. Its physical form will be changed from solids to liquid and liquids to gaseous. Only physical form of this substance will take place. No chemical reaction will be taking place in between. And this technique is based on the heat produced by the high energy electrons which are bombarding with our crucible, which is nothing but our main material, and by that this entire cluster beam evaporation will be taking place. Now we will see how it is constructed, what is its main principle, how it will be working, what kind of materials that are being used. Coming to the first material, it is that substrate. Substrate is something in which our material, a nanomaterial, a thin film will be deposited on it, and this substrate can be of different materials like glass, quartz, anything. So depending upon the substrate, our nanomaterials properties will also changes. That means if we change the substrate, the properties of nanomaterial will also changes. And the next one is a gate valve, in which it will work as a gate. For example, if any material is coming from or any material is crossing through that gate valve, it will allow those bunches which are desired, which is based on our desire, like which we wanted to make. So those bunches it will allow, and rest of them it will restrict. And the next one is a vacuum chamber. It is a chamber in which we will be removing the entire air or different gaseous present inside it. Why we are using gas chamber and what is its important and all, we will see it later. And the next one is a filament, from which, as we have already discussed, from which some electrons, some high energy electrons will be produced. As you can see here, that filament is connected to a source and it is connected to a battery. So whenever we apply some amount of energy in this entire system, from these two filaments some electrons will be transferred, and those electrons will be contributing in this cluster beam evaporation. And the next one is the crucible. Crucible is something our source material from which we wanted to make a nanomaterial. And the next one is pumping. This pumping will be mainly used for us to remove the excess amount of gases which are present inside it, or sometimes it will also include pumping of different gases like argon gas, which is of lightweight. Next one is a nanomaterial film. A nanomaterial film is a very thin film which is attached to a substrate on which our desired nanomaterials will be deposited. Now we will see how it will be working. As we have already discussed, it consists of two filaments. Here one is left side and another one is right side. Now whenever some amount of energy is passed through the source and some amount of energy is passed through these two filaments, it will releases some electrons into the crucible. Like it releases high energy electrons into the crucible, where these high energy electrons will bombard each other in all possible direction, and it will also bombard with the material which is present inside the crucible also. So because of that heavy bombardment of the electrons and the crucible, there develops a high temperature in which it increases the temperature of the walls of the crucible and as well as the material which is present inside. So when this temperature increases, the material which is present inside this crucible, that crucible will start melting. So initially it may be of the form a solid, and when this temperature is increasing because of the high energy electron bombardment, that solid will be converted into liquid, like its melting point, it will be melting. So if we again and again increases the energy from the source, the high energy electrons which are combining here, which are bombarding with each other, will also increases. So as a result, the temperature produced by this bombardment will also increases. So with that increase in temperature, the liquid so formed will again convert into gaseous. So when this solid is converted into liquid and again it is converted into a gaseous, those vapor molecules are moving freely than a solid or a liquid. So when they are moving freely, they will be coming out of this crucible using this small opening, and this small opening we will call it as a nozzle. So using these nozzles, these vapors will be coming out of that crucible and they will be spread over in the vacuum chamber. So this, why we are using vacuum here is because whenever these materials or whenever these clusters are coming out of the crucible, they may react with the gases which are present inside the chamber, which will try to add some foreign materials, or which will try to reduce the properties which we desired. So to avoid that, to avoid the reaction with some other gases, we will try to remove the unwanted gases which are present inside the chamber. So that is why we will mainly focus on keeping it vacuum. And the pumping, sometimes we have already discussed that sometimes we will be inserting some gases like argon gases which are of very lightweight. Why these kind of gases are inserted is they are less reactive and they are of very lightweight. So when they are inserted into this chamber, they will go into the bottom of that chamber, which pushes up the excess amount of gas which is present inside it. So the excess amount of gas will be coming out of that pump, and this organ gas, which is of less reactive, will be settling in the chamber. And when these when these clusters are going into this chamber, it will encounter a gate valve, in which this gate valve will allow only few few cluster of bunches to allow to pass through it, depending upon our desire, depending upon the property that we want it to be in a nanomaterial. So such clusters are passed through the gate wall, and they will deposit on the nanomaterial film which is attached to a substrate. So this entire diagram consists of two different chambers. The one is below the gate wall and the other one is above the gate wall. The chamber which is present below the gate wall is called as expansion chamber. The one which is above the gate wall, it is called as deposition chamber. And in this expansion chamber, when the cluster beam enters from the cluster source, it undergoes a supersonic expansion through the small opening of the crucible. And the next one is deposition chamber, in which it confines the cluster beam and will help them to deposit on the desired substrate. And the next one is a small abstract that I have taken from a research paper, in which it includes cluster beam evaporation technique for producing germanium nanocrystals when they are deposited on the substrate by controlling the temperature at room temperature or liquid nitrogen temperature. This entire determination or preparation of this nanocrystal is based on the cluster beam evaporation. And now coming to the advantages of this cluster beam evaporation, the first one is excellent control over the particle size. So we can construct or we can make a nanomaterial which is of our desire, how small we want, how large we want, depending upon our requirement we can able to control the size of the nanomaterial that we want to deposit on the substrate. And next one is high purity of the deposited film. So this purity is mainly because of the vacuum chamber which we are including. So this vacuum chamber, as we are removing all the entire air which is present inside, so there will be a less probability or less chances for this material to react with. So because of that, the impurities can be reduced. And the next one is low defect density. So because of this purification, clusters gently land on the substrate, because when they are crossing the gate wall, only desired amount of bunch of clusters will be going or passing through that gate wall, and they are gently depositing on the substrate. So minimal damage to the crystal structure whatever we are wanted to prepare. And next one is it reduces the dislocation or grain boundary defects as well. And the next one is low substrate temperature. So this substrate temperature is not at all matter here. Why? Because we are not using any temperature externally in this entire system. The only temperature which is increased during that vapor deposition is because of the high energy electrons. So this substrate's temperature can be minimized, or we can be able to use a temperature which is of room temperature. And the next one is independent control of growth and development. As we have already seen that we are doing this entire process in two different chambers. One is expansion chamber and the other one is deposition chamber. So this cluster formation and the deposition of this substrate will take place in two different processes or two separate processes. So one, the growth and development of this substrate will be of independent. And the next one is minimal substrate damage. That, as we have already discussed, that these clusters will go and settle down on the nanomaterial layer very gently, so it will not damage the surface of the substrate more, and there will be no ion bombardment which will be happening on the substrate. So it will cause us very less damage to the substrate. And now coming to the limitations or disadvantages of this cluster beam evaporation is, the first one is its complex experimental setup. So this entire system or this entire setup is of very complex to prepare because it includes high vacuum systems in which some materials which we are taking to produce a nanomaterial, it requires high quality of vacuum in which even if a very small amount of gas is present inside it, the nanomaterial that we wanted to make will get damaged or it will become impure. And this cluster generation chambers, skimmers, these nozzles and all are very complex to set up. And as well as we have also mentioned that it's high cost, so not even that entire system, but buying them and arranging them is also very complex. Like equipments and maintenance are also so expensive, and it also requires some skilled operations. It is not possible by some other any other person who is not aware of that complete operations. So a skilled person, the one who will be knowing about each and every step perfectly, only those people can able to perform this kind of cluster beam evaporation. And the next one is its limited scalability. Like cluster formation process is very low, so it will not include any large areas or more production. And the next one is limited scalability also. Like it will become difficult to scale up with industrial level production. So most of this cluster beam evaporation will be mainly used in research and specialized applications only. And next one is material limitation. Not all the materials from a stable clusters easily, because whatever material that are available, like, will not be suitable for this process, and metals are easier than complex compounds. And next one is high vacuum deposition. As we have already discussed, few material required ultra high vacuum conditions in which no single air molecule should be present in it. So to remove that small air molecule also, we need ultra high vacuum conditions. So that will become very difficult for us to install, and it increases the operational complexity also. The entire process may become complex. And next we'll be discussing about its current research and its future trends in cluster beam evaporation. What are the current researches that are happening on this cluster beam evaporation, and what are its future trends, how it is going to develop in future? The first one is functional nanomaterials for catalysts and sensors. So the cluster beam methods are being used to create size controlled clusters. As we have discussed, it is the size of the nanomaterial can be controlled, and that improves the performance of the activity. So these kind of things can be used in catalysis and gas sensors also. Next, broader applications in nanotechnology. Yes, we already know that researchers are exploring cluster beam to be produce materials with unique properties, nanostructured films with controlled morphology, or tailoring the surface functions for electronics, sensors, and composites as well. And the next one is computational and theoretical advances. So understanding how these clusters, like in this cluster beam evaporation, how these clusters assemble into films from a submonolayer coverage, or to fill thin film kind of growth. So how these clusters are being developed from one stage to another stage, how they are formed from the crucible, how they are combined to form up bunches, and how they are combine again to form a atom or a molecule. So this was the current topic of the research, and this deeper understanding guides optimization of deposition conditions and cluster properties. Next is interdisciplinary integration.